Okay, the next person we have presenting is Bishop Dickerson. He did a really interesting project on sonoluminescence.
Hi, I'm Bishop Dickerson, and I'm going to be talking to you guys about sonoluminescence. So when it's nighttime and you look up at the sky, what do you see? You see stars. From Earth, they're just small twinkles of light in the sky. But what they actually are giant balls of gas that are powered by fusion. Through a process called sonoluminescence, fusion may be possible by creating light from sound. So, what is sonoluminescence? Sonoluminescence is the creation of light when you theoretically pop a bubble underwater with an ultrasonic sound wave. And how it's done. So you have your bubble of air and you trap it in a flask full of degassed water. And degassed water is just water where all of the dissolved air has been removed from the water. So after you get your bubble trapped in the center of the flask, you blast it with ultrasonic sound waves, usually between 25 and 30 kilohertz. And when you get to the right amplitude, the bubble expands and pops and creates light from sound. More in depth on how it works, you have your trapped bubble. When you get to the right frequency and the right amplitude, it starts to expand. Now, there's only a certain amount of air in that bubble, so when it expands, it creates a partial vacuum. After that, if it gets big enough, it rapidly collapses, heating up all the air molecules even further and generating light and heat. So, in 2000, a species of shrimp, the snapping shrimp, was discovered to produce biological sonoluminescence. It's used for hunting to stun its prey, and what it does is it basically cocks its claw back like a gun, and it snaps it so hard that it produces a bubble and pops the bubble, creating a brief light. A brief history about sonoluminescence. It was discovered in World War II by H. Schultz and H. Frenzel. They were researching ultrasonic radar for World War II at the University of Cologne. And there were small bubbles in the water they were testing, and they started to flash unpredictably. They discovered multi-bubble sonoluminescence. 54 years of sitting in the dark, Dr. Philippe Gatillon and Professor Lawrence A. Crum found their research and picked up where they left off. Through their research, they discovered single-bubble sonoluminescence, which instead of multiple bubbles in the water, there's one bubble focused with the sound wave. Once they had finished doing what they could, Dr. S.J. Putterman picked it up, and he is the current leader in sonoluminescence. So, why would you want to do sonoluminescence? It could be a precursor to fusion. Fusion is hydrogen atoms fused together to create helium. So if you could get sonoluminescence to work, theoretically, you could have a mini sun. So, methods and materials. Mainly what I used was this diagram. It was very helpful because it has the flask and everything else shown exactly how it's set up. You get your 100 milliliter flask. You have two piezoelectric transducers on the sides that produce the sound wave, and one on the bottom that functions as the microphone. Now, it's all held by a 3-ring ring stand that needs to be held loosely so that it doesn't interfere with the vibration. Now, this is all wired up through 2 coaxial cables and 2 inductors and some resistors and a function generator and an audio amplifier so that you can generate the proper frequency and the proper amplitude so that you can pop the bubble. I use 2 oscilloscopes for mine, one for measuring the voltage and the current, and one for measuring the microphone output so I could see if I actually got sonoluminescence. After you get everything set up and you get your degassed water, well, how you get degassed water is you have to boil it for 15 minutes at a constant boil. Once it's boiled for that long, you take it off of the heat, and then you have to seal it airtight. Once that's done, no more dissolved air can get back in the water, so it creates a vacuum. After you have your degassed water, you have to very, very carefully trickle it down the side of the flask to introduce as little air back into the water as possible. Then you have your flask, and it's generating at different frequencies, and most of this time you're just experimenting with different frequencies. So you get a syringe then, and you extract a very small amount of water, enough that you can jet it back in, but not too much as to take too much water out, because you want the water to still stay spherical. So when you take the little out, you jet it back in, kind of gently, but more forcefully than just dripping the water in, to generate between 20 and 30 bubbles is what I read. And once you do that, you need to make sure your voltage and your current are in phase, which means the sine waves are aligned with each other. And once you have that, and you get the proper frequency, again, you jet the water in. And most of the times that I was doing it were unsuccessful. I could not get it to work. But one time, fairly recently, I did get it to work, and these were my results. So as you can see, the sine wave itself is distorting. When it distorts, that means that the microphone is picking up a signal more than just what the frequency generator is producing, meaning that the bubbles in the water are reacting with the sound waves. Now, what you're trying to find when you have the bubble is you're trying to find resonance. So when you capture the bubble, it distorts the waves on the microphone. Because of the bubble's rapid expansion and contraction, the microphone reads the signal as distorted because the bubble is unstable. It's not just sitting there solidly in the middle. It's unstable. And resonance is extremely important. And resonance is a frequency where the flask reacts most strongly with the ultrasonic sound waves. And when the flask is vibrated properly, the sound waves travel through the water extremely well, and they can trap the bubble. This is what the distortion should look like when you actually capture a bubble. And what I got is very close to that. So as you can see, they're very similar, but not quite the same. Now, my results. I almost captured that bubble. And it's the closest anyone at UNC has ever gotten to sonoluminescence. I found the resonance, I distorted the wave, so I almost captured a bubble. But I didn't get sonoluminescence. Now, possible mistakes I could have made. When I was looking in the flask some of the times, I noticed that there were some particles just floating around in there, and that could have introduced some unwanted dissolved oxygen into the flask of water, and that could disrupt it and make sonoluminescence not possible. Maybe I wasn't careful enough when I was trickling water down the side. Maybe when I was jetting the water in with the syringe, I wasn't careful enough. If my amplitude or frequency was off even by a little bit, it could have ruined it. And when you look at the flask, there's extremely thick glue on the sides of the piezoelectric transducers, and those could have interfered with the actual frequency and the clarity of the wave. Now, what is the future of sonoluminescence? I think it'd be very nice to measure the light and heat output to see how hot it really gets. And if you can test it with hydrogen, you can see if helium produced. And if helium is produced, that means that sonoluminescence is a fusion reaction. And it'd be very nice if you get a larger tank and higher quality piezoelectric transducers. Maybe the piezoelectric transducers could be optimized for the shape of the flask. And I would like to extend a gracious thank you to Excel Energy and the Morris Family Institute for sponsoring my research. I'd like to thank the University of Northern Colorado for hosting my research. I would like to thank the Frontiers of Science Institute for accepting me into the program and having me come here and have the opportunity to do this research. I would like to thank Kai Fitzik and Dr. Matthew Semek for their help on producing all of my results, getting all my data together, helping getting the circuit together, helping get the materials I needed. I would like to thank Karen Allnut and Chris Krause for their help, and thank you.